In our previous session, we looked at addition and subtraction. So let's look at multiplication and division. So limit as x approaches a of f of x times g of x is equal to L times m. So again, let's look at this. So limit as x approaches a of f of x means for all epsilon greater than 0 there exists a delta 1 greater than 0 such that f of x minus L is less than epsilon 1. See, I'm using epsilon 1 because in the other case I'll use epsilon 2, and then when we add them or subtract them, we will end up with another value that we'll call epsilon. Okay, and here x minus a is between delta 1 0 and delta 1. Okay, similarly, limit as x approaches a of g of x, here I missed writing equal to L, equal to m, means for all epsilon greater than 0 there exists delta 2 greater than 0 such that g of x minus m is less than epsilon 2 for all x minus a 0 less than x minus a less than delta 2. That means x minus a, absolute value of x minus a is between 0 and delta 2. Now let's take the minimum of delta 1 and delta 2, because in that case that would be applicable to both of them. So let delta is equal to minimum of delta 1 and delta 2. So therefore we can say f of x minus L is less than epsilon 1 and g of x minus m is less than epsilon 2 whenever x minus a is between 0 and delta. Now let's look at g of x. Now we can write g of x as minus m plus m. G of x minus m plus m. These two cancel out, so we still end up with g of x itself. So no issues. This we can split it up as less than or equal to, remember, triangle inequality law, g of x minus m plus m. This is less than epsilon 1. So which means we can write this as, this whole thing would be less than epsilon 1 plus magnitude of m. Again, remember, this remains as the condition. Now epsilon 1, now we always look at it from a less than 1 point of view. So we keep making epsilon smaller and smaller and smaller. So which means it is going to be less than 1. So which means epsilon 1 plus magnitude of m would be less than 1 plus magnitude of m. Again, condition remains the same. Again, let's look at f of x times g of x minus Lm. So here what are we doing? We are multiplying the limits. So let's use our normal procedure, f of x gx, and and here on the other side let me write Lm. Now in between what we'll do is we'll introduce minus Lgx plus Lgx. So again we end up with the same term, so the value doesn't change. Okay, so here g of x is common, so let's take it out. So f of x minus L plus here L is common, so L times g of x minus m. Let's split them up. So which means this is going to be less than or equal to g of x times f of x minus L plus L times g of x minus m. Now remember g of x, see here, g of x we can write it as, right, so g of x is less than 1 plus magnitude of m, is less than 1 plus magnitude of m. This is less than epsilon 1, so which means this whole thing would become less than, and similarly this is less than epsilon 2. So that means the whole thing would be less than 1 plus magnitude of m epsilon 1 plus magnitude of L times epsilon 2. Now let's say here we have kept epsilon 1 is equal to epsilon 2, right? That means we are taking the same value of epsilon in both the cases, that is of f of x and g of x. In that case, we can write this as 1, because this and this would become common. We can write it as 1 plus magnitude of m plus magnitude of L and epsilon 1. Now when we reach this stage, remember, don't forget all this is beginning with this. So which means now let's rewrite the entire statement. F of x times g of x minus Lm is less than 1 plus magnitude of m plus magnitude of L times epsilon 1. Now what we'll do is we have to make sure that this gets cancelled off. So let us say epsilon 1 is equal to epsilon by 1 plus magnitude of m plus magnitude of L. So what will happen if we do the substitution? We'll end up with f of x times g of x minus L times m is less than, this and this will get cancelled out and we will be left with epsilon. And the condition still remains. What is that? X minus a is between 0 and delta. So what does this statement imply? This implies limit as x approaches a of f of x times g of x is equal to Lm. Okay, so that is multiplication. Then we come to division. So we have to show that limit as x approaches a of f of x by g of x is equal to L by m, and of course here m is not equal to 0. Now first what we'll do is we'll look at we'll ignore f of x and L. First we'll try to prove that limit as x approaches a of 1 by g of x is equal to 1 by m. Then it's just a question of multiplying. So let's begin. Limit as x approaches a of g of x is equal to m, which implies there for all epsilon 1 greater than 0 there exists delta 1 greater than 0 such that g of x minus m is less than epsilon 1. X minus a is between 0 and delta 1. Let's take m. In case of multiplication we took g of x, right? But here we are taking m. This we can write it as m minus g of x plus g of x. So the value still remains the same. Now let's split this up. So we can say this is less than or equal to m minus g of x plus g of x. And remember, since we are talking of absolute values, it doesn't matter in which order we do the operations, right? So we can rearrange this plus g of x. What is this? This is less than epsilon 1. So this implies magnitude of m is less than or equal to epsilon 1 plus magnitude of g of x. Now this implies epsilon 1 plus g of x is greater than the magnitude of m, which implies g of x magnitude is greater than magnitude of m plus minus epsilon 1. Again, we still keep carrying the condition. It's between 0 and delta 1. Now, let's say epsilon 1 is equal to magnitude of m by 2. In that case, what happens? G of x magnitude becomes greater than magnitude of m minus magnitude of m by 2, which is 2 magnitude of m minus magnitude of m gives us magnitude of m by 2. So magnitude of g of x is greater than magnitude of m by 2, which means, let's take the reciprocal of this. We get 1 by g of x is, since we are taking reciprocal, the sign changes, less than 2 by magnitude of m. Now let's take the reciprocal of this. So this becomes, we can actually leave 1 as it is and take the magnitude of g of x is less than 2 by magnitude of m. Yes. So this is one of our results, intermediate results. Now what we are going to do is we are going to again look at the same statement as x approaches a of g of x equal to m. This implies for all epsilon 1 greater than 0, there exists another delta greater than 0 such that g of x minus m is less than epsilon magnitude of m square by 2. Now why are we taking this odd kind of figure? This here, we know that there is a figure like this, right? So in the denominator, at some point in time, we will end up with magnitude of m. Our ultimate objective is to get less than epsilon. So that means magnitude of m has to get cancelled. The 2 also has to get cancelled. So that is why we are. Now the question comes, y square. Just imagine the person who gave this proof for the first time. He would have, not got it right in the first. He would have gone forward, then realized something, come back, made some changes to this, again gone ahead, then come back again, right? So through trial and error method, this figure has been arrived at. It's not as if in one shot they have got it. Okay, so why we are taking this? So that at a later point in time, cancellations can happen. Again, condition is what? X minus a is between 0 and delta 2. Okay, now let's take the minimum of delta 1 and delta 2. Let's say delta is minimum of delta 1 and delta 2. So which means we can write the statement as 1 by magnitude of g of x is equal to 2 by magnitude of m and the condition now becomes is between 0 and delta, not delta 1 and delta 2. Similarly, g of x minus m is less than epsilon magnitude of m square by 2. Again for the same condition. Again 1 by g of x minus 1 by m. This is what we want to prove, right? Is less than epsilon. Now this can be written as m times g of x. We are taking the LCM and doing it minus m minus g of x. Now since magnitude is there, we can write it as g of x minus m, and in the bottom we can split it up into magnitude of m times magnitude of g of x. Okay, now this is going to be less than what? G of x minus m is less than this, right? So this is less than epsilon magnitude of m square by 2 divided by magnitude of m by 2 times magnitude of m is already there. Now this can be written as m square by 2 times 2 by magnitude of m square. So these two get cancelled, these two get cancelled. So here on the left hand side, what do we have? We have 1 by g of x minus 1 by m is less than. Similarly, 1 by g of x minus 1 by m is less than this. So what do we end up with? 1 by g of x minus 1 by m is less than epsilon for the given condition. Minus x of x minus a is between 0 and delta. This implies what? This implies limit as x approaches a of 1 by g of x is equal to 1 by m. So this is our intermediate proof, partial proof. And now finally, limit as x approaches a of f of x by g of x is equal to, now we can write this as limit as x approaches a of f of x times limit as x approaches a of 1 by g of x. Now this is equal to limit of f of x is what? L times limit of 1 by g of x is what? 1 by m. So therefore, limit as x approaches a of f of x by g of x is equal to L by m. And general rule, the denominator cannot be equal to 0. So here the tricky parts were what? The tricky parts were when we say let this be something, and that something is crazy, right? So here this is okay. Where is that? Let magnitude of m equal to this. But to arrive at this also it takes, okay, this is how we have to start. How do we, how does the person who wrote it first think of all this? Basically they just, keep doodling, keep trying out different ways of going forward. So this is what I was saying. Let epsilon 1 equal to magnitude of m by 2. Why magnitude of m by 2? As I said before, it's all trial and error. Okay, so that is why you need to practice a lot more if you are interested in proving it. But if you are just interested in using it, then that's a different story altogether. I think that's enough for today. Bye for now.